Bismillahirrahmanirrahim. Assalamu alaikum. I am Dr. Syed Salman Shafqat with you in this lecture number 6. Uh, Initially, I prepared my lectures in a combo of Urdu and English, but the authorities and committee that is developed by our university to approve lectures before sending the students have rejected my lectures because of usage of Urdu language. That's why I am going to prepare my this lecture in full English version. But anyhow, if any student needs these lectures in Urdu and English mixed mode, they can also contact me, and you can also take the PDF of these lectures from me. So anyhow, now we are going to move. Here are the key points of this lecture. In this lecture, actually, we are going to discuss ferromagnetic materials. Before going into details of ferromagnetic materials, we must know the basis of Curie temperature. From the Curie temperature, we shall develop concept of hysteresis loop, and from hysteresis loop there are two other terms that are related to this hysteresis loop, and those terms are known as coercivity and remanence. So after having complete understanding of these terms, we will be able to develop our concept regarding ferromagnetic materials, and then we shall discuss about a structure of well-known, and I think so, the first known magnetic material, that is magnetite, and at the end we shall see about antiferromagnetic materials, and at the last I have posted few questions regarding this lecture. What is Curie temperature? Even though electronic exchange forces in ferromagnets are very large thermal energy eventually overcomes the the exchange and produces a randomizing effect. This occurs at a particular temperature that is called as Curie temperature. Below Curie temperature, ferromagnets are ordered, and above it, disordered. The saturation magnetization goes to zero at the Curie temperature. A typical plot of magnetization versus temperature for magnetite is shown in the next slide. The Curie temperature is an intrinsic property and is a diagnostic parameter that can be used for the mineral identification. However, it is not foolproof because different magnetic materials in principle can have same Curie temperature. So actually I want to develop a base for moving to my next topic. Here I want to explain to you that there are electronic exchange forces in ferromagnetic materials. But in case of paramagnetic materials, the magnetic moments or domains are independent from each other. They have no interaction within crystal lattice with each other. However, when we apply magnetic field on a paramagnetic material, applied magnetic field tends to align all the magnetic domains in its own direction, and material get magnetized, and material only exhibit magnetization in the presence of applied magnet. Now I'm going towards ferromagnets. In ferromagnets, the magnetic domains are interacting with each other. The electrons or domains or moments, whatever you can use the term, because different theories use different terminologies. They interfere with each other, they exchange their forces, and mostly the forces that are being exchanged by these domains are electronic exchange forces. These electronic exchange forces tend to align themselves and about the origin of ferromagnetism we have discussed in our previous lecture according to classical theory as well as according to Heisenberg's concept. According to classical theory, the source of ferromagnetism is presence of magnetic domains in a parallel alignment, and according to Heisenberg's concept, the source of ferromagnetism is exchange forces. So, when a ferromagnetic material will be placed in applied magnetic field, it will enhance their magnetization. But if we apply temperature, temperature will have an inverse effect on magnetization because it will provide kinetic or potential energy, and it will distribute and try to produce a randomizing effect on the materials, and ultimately material will lose its magnetization. Curie temperature is particular for different materials, as I told about Curie temperature of three materials: iron, cobalt, and nickel in my last lecture. I think so. Iron has Curie temperature about 770, nickel has 11,100 and something, and the third material, nickel, has Curie temperature about 358, something like that. You can get the data from previous lecture. So different materials have definite value of Curie temperature, and it's also a tool to detect minerals and metals. But it is also being mentioned here that it's not a foolproof tool because some of the materials can have their Curie temperature in similar range. Here, as I told you in previous slide, that effect of temperature on magnetization of paramagnetic materials as well as ferromagnetic materials. Both of the materials lose their magnetization, or we can say the magnetization of these materials has inverse relation with the temperature. Here I use the term magnetization, but you can also say effect of temperature on magnetic susceptibility or magnetic moment or magnetization, because magnetization is a very general term. The proper terms are magnetic susceptibility or magnetic moment. So we can see on the x-axis is temperature and y-axis is representing magnetization or magnetic susceptibility, and red color curve is showing that initially when the temperature is zero and magnetization is unity, and when we move along x-axis, means as the temperature increases, the red curve is showing a downfall. It means magnetization of paramagnetic and ferromagnetic material has inverse relationship with temperature. Hysteresis. What is hysteresis? In addition to Curie temperature and saturation magnetization, ferromagnets can retain a memory of applied magnetic field when it is removed. The behavior is called hysteresis. For paramagnetic materials, there is no magnetization after the removal of applied magnetic field. They are nor magnet before the application of magnetic field, and neither after the removal of a magnetic field. But ferromagnetic materials are magnets in the absence of magnetic field. They are magnets in the presence of applied magnetic field with enhanced magnetization, and they will be magnet with enhanced magnetization after the removal of magnetic field. And how much magnetization is stored in them after passing through an applied magnetic field, this is known as hysteresis. This whole process is known as hysteresis. A plot of variation of magnetization with the magnetic field is called as hysteresis loop. Another hysteresis property is coercivity of remanence. Here is this is the reverse field which when applied and then removed reduces the saturation remanence to zero. It is always greater than coercive forces. Remanence, that is represented by Mr, is the residual magnetization that remains after the material is first saturated in magnetic field and then the field is reduced to zero. इसका मतलब ये है कि हमने मटेरियल को फेरोमैग्नेट मटेरियल एक मैग्नेट होता है, इसको जब हम मैग्नेटिक फील्ड में रखते हैं तो इसकी मैग्नेटाइजेशन बढ़ जाती है। जब हम उस मटेरियल को मैग्नेटिक फील्ड से बाहर निकाल लेते हैं तो उसके अंदर अप्लाइड मैग्नेटिक फील्ड के कुछ असरात रह जाते हैं। अब वो किस कदर उसके अंदर मैग्नेटाइजेशन स्टोर हुई है मैग्नेटिक फील्ड के इफेक्ट से, उसको कहा जाता है रेमिनेंस, और या इसको कहा जा सकता है रेजिडुअल मैग्नेटाइजेशन। दिस इज अ schematic representation of hysteresis loop. We shall start this hysteresis loop from the zero. So hope so you can see the moving cursor of my lecture at this point, where the x and y axis have zero values. So you can see from the center the line going upward and it reaches to a maximum point. I'm talking about the middle arrow that is going upward. So uh, by the increasing magnetic field that is shown on x-axis, the magnetization is goes on increasing and it reaches at maximum level, that is ms. You can see along the y-axis is representing magnetization and x-axis is representing magnetic field. So once the material has been reached to its maximum saturation magnetization, so then we have to we account its demagnetization. So when we decrease the field strength, definitely material will uh, decrease its magnetization, and you can see the curve that is bisecting the y-axis, means the first curve with downward arrow, the material is going downward, and you can see the arrows showing magnetic remanence and HC is coercivity. So this is a full uh, diagram, means from material's original magnetization. Once we apply magnetic field and it goes on increasing up to a certain maximum level, and then we goes on decreasing the magnetic field and it will come towards its minimum level. Uh, I have shared some links at the end of this lecture. On those lectures, you can see a very beautiful, colorful picture that is representing the material with hysteresis loop. I don't know why when I captured the picture, it becomes black and white. But on the links that I have shared at the end of this lecture, from those lectures you can see the colored image of this picture. In that picture, each curve has different curve and easy to visualize and easy to understand. The initial susceptibility, that is psi 0, is the magnetization observed in low fields on the order of the Earth's field, that is from 50 to 100 mu Tesla. The various hysteresis parameters are not solely intrinsic properties but are dependent on grain size, domain state, stresses, and temperature. Because hysteresis parameters are dependent on grain size, but they are useful for magnetic grain sizing of natural sample. Coercitivity, sorry, coercivity. Magnetic coercitivity, coercive field or coercive force is a measure of ability of ferromagnetic material to withstand with an external magnetic field without becoming demagnetized. Coercitivity in ferromagnetic material is the intensity of applied magnetic field required to reduce the magnetization of material to zero after the magnetization of sample has driven to saturation. Thus, normal coercivity measures the resistance of a ferromagnetic material to be to becoming demagnetized. इसका मतलब ये है कि मटेरियल को हमने मैग्नेटाइज कर लिया, अब उस मटेरियल को डीमैग्नेटाइज करना है। अगर तो मटेरियल फौरी तौर पे डीमैग्नेटाइज हो जाए तो इसका मतलब ये है कि वो एक अच्छा मैग्नेट नहीं है, और अगर वो उसको दोबारा से डीमैग्नेटाइज करने के लिए हमें बहुत ज़्यादा एफर्ट करनी पड़े, इतनी आसानी से वो वापस ना आए, तो इसका मतलब क्या है कि वो एक मटेरियल अच्छी खसूसियात का हामिल है कि वो एक अच्छा मैग्नेट बन सकता है। अब अच्छे का मतलब ज़रूरी नहीं है कि जो जिसके अंदर मैग्नेटाइजेशन हो वो बहुत अच्छा मैग्नेट है। समटाइम्स ऐसे मटेरियल की ज़रूरत होती है कि जो फौरी मैग्नेटाइजेशन लूज़ करें, समटाइम्स ऐसे मटेरियल की ज़रूरत होती है कि जो परमानेंट मैग्नेटाइजेशन रिटेन करें, तो वो ज़रूरत पे डिपेंड करता है। Measurement of coercivity. Coercivity is usually measured in Oersted or amperes per meter, and its unit is denoted by Hc. A large value in intrinsic coercivity, which does not take into account the negative vacuum permittivity contribution to the magnetic field, only considering the magnetization. This may be ambiguity between the two concepts, and especially for strong magnets, the difference becomes significant. The strongest rare earth magnets lose actually almost none of the magnetization at Hc, and the reduction of the field to zero is almost equal to the contribution of the vacuum permittivity to the magnetic field. Now we shall come towards two types of materials. There are two classification of materials based upon their coercivity and remanence. These two classes are magnetically hard materials and magnetically soft materials. The normal coercivity is used to calculate the magnetomotive forces, while the intrinsic coercivity is used to assess the sensitivity to demagnetize. It can be measured using BH analyzer or magnetometer. Ferromagnetic materials with high coercivity are called magnetically hard and are used to make permanent magnets. On the other hand, the materials with low coercivity are said to be magnetically soft. The latter are used in transformers and inductive cores, in recording heads, microwave devices, and other magnetic shielding materials. Coercivity. It must be driven back to zero by a field in the opposite direction. The amount of reverse field required to demagnetize it is called coercivity. If an alternating magnetic field is applied to the material, its magnetization will trace out a loop called hysteresis loop. The lack of retraceability of the magnetization curve is the property called hysteresis, and it is related to the existence of magnetic domains in the material. Once the magnetic domains are reoriented, it takes some energy to turn them back again. This property of ferromagnetic material is useful as magnetic memory. Some compositions of ferromagnetic materials will retain an imposed magnetization indefinitely and are useful as permanent magnets. The table contains some data about the materials used as uh, permanent magnets. The table is presented on the next slide. Both the coercivity and the remanence are quoted in Tesla, the basic unit for magnetic field. B. The hysteresis loop plotted in the form of magnetization as a function of driving magnetic field strength. The practice is commonly followed because it shows the external driving influence H on the horizontal axis and response of the material on the vertical axis. Besides coercivity and remanence, a quality factor for the permanent magnet is quantity B naught over mu naught maximum. A high value for this quality implies that the required magnetic flux can be obtained with a smaller volume of material, making the device lighter and more compact. Here are some materials. Their coercivity, remanence, and the other factor BP naught over mu naught maximum has been described. We can see for the first material, their coercivity and remanence are the same. Similarly, for L Nico, the values are very close to each other. For L Nico 5, the values are not in similar range. And for the last materials, the values of both of these factors are equal. A good permanent magnet should produce a high magnetic field, having low mass, and should be stable against the influence which would demagnetize it. The desirable properties of such magnets are typically stated in terms of remanence and coercivity of magnets. When a ferromagnetic material is magnetized in one direction, it will not relax back to zero magnetization when the imposed magnetic field is removed. The amount of magnetization is retains at zero driving field is called its remanence. The alloys from which permanent magnets are made are often very difficult to handle metallurgically. They are mechanically hard and brittle. They may be cast and then ground into shapes over or even ground to a powder and formed. From powders, they may be mixed with resin binders and then compressed and heat treated. Maximum anisotropy of the material is desirable so that the end material are often heat treated in the presence of a strong magnetic field. The materials with high remanence and high coercitivity from which permanent magnets are made are sometimes said to be magnetically hard, to, cross, to contrast with the magnetically soft. Materials from which transformer cores and coils of electronics are made. The permanent rare earth magnets, the permanent magnets which have produced the largest magnetic flux with the smallest mass are the rare earth magnets based on samarium and neodymium. Their higher magnetic fields and lighter weight make them useful for demonstrating magnetic levitation over superconducting materials. So the picture is representing these two metals, that is samarium and neodymium. The samarium cobalt combination have been around longer, and samarium cobalt 5 magnets are produced for applications where their strength and smaller size offsets and disadvantages of their high cost. The more recent neodymium material like Nd twice F14 boron produce comparable performance, and the raw alloy material cost is one-tenth as much. They have begun to find applications in microphones and their applications that exploit their high field and light weight. The production is still quite costly since The raw alloy must be ground to powder, pressed into desired shape, and then sintered to make a durable solid. Here, a term that is sintering. Sintering is actually a process in which we react to solid powder materials without passing them through liquid state. Usually, the reactions we conduct in our chemistry laboratory, they are conducted in different solvents, and usually the solid materials cross their melting point and they react and produce a new product. But the sintering is something we mix or react different powders in a furnace without any solvent, and those powders or materials mix together. Something very common example for sintering I can give you. A common example is the ceramic tiles that are used for the flooring for the bathrooms. They are produced through sintering process. Now we shall come towards the structure of a material that is magnetite. Magnetite is a ferromagnetic material. Magnetite Fe3O4 crystallizes with the spinel structure. The large oxygen ions are closed, packed in cubic arrangement, and the smaller oxygen ions are filled in the gaps. The gaps come into two flavors, tetrahedral sites and octahedral sites. Iron ion is surrounded by four oxygens, and in octahedral site, iron is surrounded by six oxygens. The tetrahedral and octahedral sides form the two magnetic sublattices A and B respectively. The spine on the A sublattice are anti-parallel to those on B uh, sublattices. The two crystal sites are very different and result in complex form of exchange interactions of the iron ions between and with the two types of sites. The structural formula for magnetite is Fe3 positive in crystal lattice A and Fe3 plus Fe plus 2 in crystal lattice B and mediated by four oxygen atoms. This particular arrangement of cations on the A and B sublattices is called an inverse spinel structure. With negative AB exchange interactions, the net magnetic moment of magnetite is due to B side due to Fe plus 2 ion. Ferrimagnetism chiefly occurs in magnetic oxides. The natural magnetism exhibited by lodestone, recorded as early as the 6th century, is that of ferrite. The mineral magnetite, a compound containing negative oxygen anion, oxygen having -2, and positive iron ion in two states, iron 2 and iron 3. The oxygen ion are not magnetic, but both iron ions are magnet. In magnetite crystal, chemically formulated as Fe3O4, for every 4 ions there are 2 iron ions with +3 oxidation state and 1 iron ion with +2 oxidation state. The iron with +3 oxidation state are paired off in opposite direction and producing no external magnetic field. But iron 2 ions are aligned in the same direction, accounting for the external magnetism. The spontaneous alignment that produces ferrimagnetism is entirely disrupted above a temperature called as Curie point. Characteristics of each ferrimagnetic material. When the temperature of material is brought below Curie temperature, ferrimagnetism revives. Here is a representation of model of magnetite. One, one picture is showing the geometry of bulk material, and a simple diagram that is on right hand side is clearly showing two types of ions connected to oxygen atoms. The red colored mark iron ion is tetrahedrally attached to 4 oxygen atoms, and the yellow colored iron that is connected to 6 oxygen atoms in a octahedral fashion. This octahedral geometry is also known as tetragonal bipyramidal. So from this diagram, the geometry of magnetite is very clear. So we can see that chemical composition of magnetite is ferrous, ferric, and 4 oxygen atoms. In short, we can say the chemical composition of magnetite is Fe plus 2, Fe2 plus 3, and O4. The structure is inverse spinel with oxide ions forming a face-centered cubic lattice and the iron cations occupying interstational sites. Half of the uh, iron plus 3 cations occupy tetrahedral site, while the other half, along with plus 2 iron cations, occupy octahedral sites. Here are the links that I told you. From these links, you can get further details of this lecture. And at the end, here are the questions from this lecture. What is hysteresis loop? Explain structure of magnetite, and what is different between uh, hysteresis? Sorry, what is difference between coercivity and reminence? I would like to say thank you so much for listening. For any question, query, you feel free to ask me on WhatsApp, on Google Meet, and on any type of contact details